With this screencast, we will complete Chapter 7. As you can tell from this chapter, there's an awful lot of astronomy and what we would call astrophysics in this chapter. For those of you that are interested in this, I do have one former student from years ago who works extensively with NASA, her name is Natalie, and she was interested in physics and astronomy and astrophysics from the first time she took one of my classes. I think it was in honors chemistry. In any case, you might recall equation 7.22, which is this one right here. And just a reminder about how we get variations of Newton's universal law of gravity. The universal law of gravity began looking like this: m1, m2, over the distance between them squared. If we multiply both sides by r, we get force times r equals g m1, m2 divided by r. And you should recognize that a force times a distance is also known as work, which is a form of energy, and vice versa. And here we're talking about the potential energy because we're doing work to lift something off of the surface of the earth against its gravity, or if it's coming back down to the earth, we say that the Earth's gravitational field is doing work on the object as it falls. So this derivation here is where we got equation 7.22. Now, this equation, what we're going to derive down here, is mgh, the simplified version of potential energy, which is only true when h is very, very small compared to the distance that an object is way far from the earth. When h is very small, meaning you're very, very close to the surface of the earth. So as we do the derivation, we have our change in potential energy as we're going from way out here and we're falling all the way down to here. And so we have this variation of the equation minus this variation of the equation of Newton's universal law of gravity equation in order to find my change in potential energy. I would probably draw it like this. My change in potential energy looks like that. And then we distribute the g, mass of the earth, times the mass of the object that is way out in space. Now, my height is going to be the radius of the earth plus the distance above the earth, and that's for an object way far away. And then for an object near the surface of the earth, way down here, if you're near the surface of the earth, for all intents and purposes, your height above the surface of the earth, which might only be a few or 10 or 20 meters, doesn't even show up in the sig digs when you have the radius of the earth. So it's just RE. Now, coming down to the next part of our math, because if we distribute the RE, we get this term right here, RE times the binomial RE plus H. And if we remember that H, again, can be dropped from the second factor in the denominator when H is very, very small. When H goes to 0, in other words, or is practically 0, we end up with R, radius of the earth, squared. This is a reasonable approximation because the radius of the earth is much, much bigger than most objects that are going to be in the vicinity of the earth and falling, even if they're falling from something being dropped out of a hot air balloon or an airplane. Then, as we continue to simplify this equation, you might remember that g from earlier is this value right there. And where did we get this equation from? Well, I'm going to go ahead and erase all of this And we're going to take the universal law of gravity again. F equals G times m1, m2 over the distance between them squared. And this force is going to be ma. And we're going to cancel out the small masses, where the other mass is the mass of the Earth. And we've canceled out the m out of this. And that's where we get this acceleration, which is g, equaling g times the mass of the Earth divided by the radius of the Earth squared, right there. And so since that is g, if all of this right here is g, we get your potential energy equals mgh. So we've taken the more universal universal observation of changes in potential energy around planets and stars and things like that, and reduced it to its simple case. Now, another interesting phenomenon is something that is called the escape speed. Now, we've already talked about the minimum speed you need to maintain to stay in orbit around the Earth or a planet around the sun. You don't want a speed too great because you'll get slingshot into space. You don't want a speed too low because then you're going to plummet into the Earth's atmosphere or into the star, whatever you're orbiting. So we were talking about the minimum speed to stay in orbit. This is a different type of speed. This is called the escape speed. And from the perspective of the Earth, because it's going out in all different directions wherever you're trying to take off from the Earth, we usually think of it as a speed as opposed to a velocity. In any case, what we're going to do in order to calculate what is this escape speed is we're going to begin with what is the energy. Here's my work energy theorem. We're going to begin with the kinetic and potential energy that my object has on the surface of the Earth, and then we're going to launch it into some distance above the Earth and find out its kinetic and potential energy up there. Now, because we're planning on going so far out into space that we are outside of the Earth's gravitational pull, that means there's no unbalanced force acting on the object, which would be the gravitational force of the Earth, and therefore it's going to have its speed is going to reach zero when the object is an infinite distance away. And so that means my potential energy on the surface of the Earth is zero, and when I'm at an infinite distance from the Earth and no longer trying to get away from the Earth's pull, the kinetic energy goes to zero. And so my initial kinetic energy, which is 1/2 mv squared, equals this much energy here. And when we solve for v, we find that this is my escape speed, at least to escape from the surface of the Earth. We would have to put other masses of other planets in there if we were trying to escape from something else. And we'd also have to have a radius of that other planet, Jupiter, Saturn, Neptune, Uranus, Mars, whatever. And so when we look at this chart over here, you can see that the escape speed for the Earth is 11.2 kilometers per second. Another thing you should notice is it doesn't matter what the mass is. Whether you want the object is a spacecraft or a molecule, it doesn't matter. Its escape speed is going to be 11.2 kilometers per second. You'll notice that Venus's is just about the same. So we could expect that because the Earth has an atmosphere, so should Venus have an atmosphere. And indeed it does, but it's predominantly carbon dioxide. So that place is really, really hot. Now, a very, very small planet like Mercury, or a non-planet like the Moon, and even Mars. These escape velocities are quite low. They are less than half that of the Earth, which means it's much, much easier for smaller molecules to escape. The escape speed of the Earth is just fast enough for big molecules. I should say is just fast enough so that the smaller molecules, like oxygen gas and nitrogen gas, can't escape. But the smallest of molecules, like hydrogen and helium, do. Obviously, we wouldn't want to have the speed so much that we're throwing oxygen and nitrogen off the surface of the planet. So the Earth's mass has to be just right, part of the Goldilocks principle, one of the hundreds and hundreds of parameters that must be exactly right for the Earth to be suitable for life. This is again why we do not have any atmosphere on the moon or on Mars. Now, you also have to have a source to produce those gases, and then enough gravitational pull and slow enough escape velocity so that you don't lose them. Now, coming down here, this is where they talk about Mercury and Venus, and I think I just did that. So let's take a look at this problem right here, from the Earth to the Moon. Now, they refer here to one of my favorite authors way back in middle school. I think it was, I read most of the books by Jules Verne. He wrote during the middle of the 19th century. He was a Frenchman, very interesting person. And some of the books you might have heard about, Around the World in 80 Days. There was a movie on that. There was Journey to the Center of the Earth. There was a movie on that. 20,000 Leagues Under the Sea. There was a movie on that. Those are some of the books. And one of the books was From Earth to the Moon. 1865 was when he wrote this, at the end of of course, in our country, that would have been right at the end of the Civil War. And he used the science of the day. He really tried to make his novels match the science as well as we understood things 150 years ago. So this problem says if we dug a hole in Florida to make it like a big cannon, and we are going to launch a spacecraft out of that giant cannon that's in this deep hole in the Earth, and shoot a spacecraft at the moon, and that's what the story is about. Well, let's just test that with what we know today to see whether or not that is feasible. So if the spacecraft leaves the cannon at the escape speed, so somehow this cannon has a sufficient enough charge to propel an object out of it at 11.2 kilometers per second, which is this many meters per second. Please notice, folks, that we want to be consistent with our dimensions, and since we're working with joules of energy, we have to be in meters, not in kilometers. Our masses have to be in kilograms and not in grams, because we're in the MKS metric system. So the K is in kilograms, the M is meters. Now, we want to find the speed of this satellite or this spacecraft that we're launching when it is 1.50 times 10 to the fifth kilometers above the surface of the Earth. So again, we're going to do our work energy theorem. And so we have our kinetic energy, and we have our potential energy, and then our kinetic energy and our potential energy. And we're going to bring this term over to here, and you can see that the masses are going to cancel out. And then if we multiply by 2, we get the fractions to cancel out. 2. This is going to cancel out, and we're going to get a 2 over there. And so now we're down to this equation right here. And if we solve this equation for the final velocity, and we plug in the escape speed in meters per second, not kilometers per second, and here's my universal constant, gravitational constant. Remember, that's a capital G, not to be confused with gravity, which is a lowercase g. We find out that this final velocity at this altitude of 1.5 times 10 to the fifth kilometers is 2.39 times 10 to the third meters per second. So in order to find the acceleration through the cannonbore, so here's the surface of the Earth. We've got a hole in it, and the hole goes down here. And what we want to do is find the acceleration from start to finish as it exits the hole in the Earth where the cannon happens to be. And then our satellite is going to come flying off and go towards the moon. And of course, the moon, we want to be happy moon. So you might remember this kinematic equation way back from chapter 2. So we simplify it and subtract the initial velocity squared from both sides. Well, the initial velocity squared, of course, is going to be 0 because we're starting at rest. And when we plug our numbers in, and we want it to have this escape speed, we find out that, and this is going to be the, this is the bore, the length of the cannon. This is the length of the cannon, 1 kilometer, 1,000 meters. We find out that the acceleration is 6.27 times 10 to the fourth meters per second. In other words, it's 6270 Gs. Now, if you think about it, when you're in a commercial airline and you get ready to land, and as soon as you land, they try to stop pretty smoothly, but rather quickly because you don't want to run off the end of the runway, you're experiencing about a G horizontally, just like you're used to vertically from the Earth's gravitational pull. Now, if you are taking off in a jet airplane, you might take off with a couple of Gs, 2 or 3 times the acceleration due to gravity. A astronaut in a big space rocket might experience 1.5 to 2 Gs because it's a little bit more gradual with those monstrous engines launching you into space. A fighter pilot who is very, very skilled and trained well and has the right physical constitution, they can actually experience maybe 7 to 9 Gs. Think of Tom Cruise in Top Gun 2. The most Gs anyone has ever experienced is when you come to a very, very rapid screeching halt, which is usually not a good idea to come to a halt in a short period of time. But people have survived 30, 40 Gs with that when you come to a halt very, very fast. A couple of points here. I already talked about this one right here. Here's 2 vocabulary words if you like astronomy. Because no orbit around a star or no orbit of the moon around a planet is perfectly circular, though some are pretty close. The nearest point in the elliptical orbit is called the perigee, and the farthest point is called the apogee. The last thing we want to talk about are Kepler's laws, of which there are 3. Now, this is some very interesting history. And it goes back all the way to the time of the Greeks with the Ptolemy geocentric model. Now, geocentric means, geo means earth, centric means in the middle. It was believed that the earth was at the center of the universe. And that idea, based on Greek astronomy, held sway for 1,400 years. In other words, beginning from before the time of Christ, probably a little bit, to the time of Ptolemy, who was a couple centuries after Christ, all the way till a couple of astronomers, a few centuries beginning to get an inkling of an idea before Copernicus, to this period of time right here, nobody really challenged this. And then along comes Nicholas Copernicus, and he begins to say, I think that the sun should be at the center of the solar system and not the Earth. And everyone thought that was kind of interesting. It was a little radical. They didn't see any need to switch gears as far as the Ptolemaic approach was concerned. Copernicus was a Catholic Christian, and his proposal of the heliocentric model was interesting. It didn't gain a whole lot of sway. And then along comes Tycho Brahe, and about the same period of time, and he's making these incredibly accurate astronomical measurements over much of his lifetime, or 20 years of his lifetime. He didn't, or at least live all that long. And he didn't have the fanciest of instruments back then. In fact, they didn't even have a telescope back then. But his measurements were so good of the planets and 777 stars that when Johannes Kepler came along, he said, as he was analyzing that data, that the only way to explain that data, as he spent 16 years trying to deduce a mathematical model for it, was to have the sun at the center of the solar system, just like Tycho Brahe did. And in order to keep the Earth at the center of the solar system, some of the planets had to do this. They had to sometimes appear, since they appeared from the Earth to go backwards over certain periods of time, they invented the concept of epicycles. And the Ptolemaic model got more and more clumsy and awkward. And so finally it was replaced by Kepler's idea, with help from Galileo along the way. And of course, there's a lot of mythology that has developed about Galileo, who was never really persecuted or anything like that. And it was not Galileo and Copernicus, the men of science, versus Christianity, or not even necessarily certainly not religion in general. But Galileo was a Christian, though not the nicest of characters. Copernicus was a Catholic Christian. Johannes Kepler, a Lutheran, was a very, very devout Christian. You should see and read some of the things that he wrote were just glorious. He's the guy that said that we actually are thinking God's thoughts after him as we study his creation and try to deduce equations and reconcile observation with math. Now, one of the cool things about Johannes Kepler and his attention to detail was that when he finally developed some mathematical equations, his math and his observations for Mars were off by 8 minutes. In other words, his math said that the planet should be in such and such a location. His observation showed that it was not there, but it was awful close. It was just 8 minutes away. And I think most people would say, boy, that is really, really good. We're just going to let that ride. But that was not good enough for Kepler. He believed in a God who was very, very precise. He did not believe in sloppiness, if you will. He said there's got to be a reason for this 8 minutes. And when he got rid of the circular orbit, again, that's a holdover from Greek philosophy where circles were perfect trajectories or pathways for planets, and replaced it with an elliptical one. I shouldn't erase that. When he replaced it with an elliptical one, the 8 minutes were gone. And the physical observation of Mars and the mathematical prediction of where Mars should be matched perfectly. Newton then, another devout Christian, but also didn't have the greatest of character, pretty much a loner, and a bit cantankerous. In any case, he built on Kepler's laws, and that's where we end up with the universal law of gravity and the Newton's laws of motions and things like that. So what are Kepler's laws? And there are three of them right here. And the first one I already mentioned, that planets move as ellipses and not as circles. Because it was true for the for the Earth going around the sun and Mars for that matter, those orbits are almost circular. I mean, you almost couldn't draw a more perfect circle, or even maybe with the compass draw a more perfect circle than the Earth seems to make around the sun. But indeed, it is elliptical, not perfectly circular. Number two, a line drawn from the sun to any planet sweeps out equal areas in equal time intervals. Well, first of all, let's talk a little bit more about an ellipse. So this is number one, and then down here is where we're going to talk about number two. So you should know what an ellipse is. If I were on the marker board, I would get a piece of string, and I would tape one end to the marker board and the other end of the marker board so the string was limp and loose. And so let's say it's dangling down like that. And then I would take my marker and I would make the string taut, like that. So it's no longer curved. So the string is a fixed length. And then as I move my pen, and let's say I move my pen to another location, let's say from there to there, the blue line, including the bend in it, the blue line is the same length as the red line. And then let's say I went from there to there. And then let's say I went from there to there. No matter where I went, as long as I kept the string taut, I would create an ellipse. And the two places where the string is taped, there and there, are called the focus points, or foci for plural. Now, the planets go around the sun in elliptical orbit. Generally not nearly as elliptical as this, but we're exaggerating here to make a point later on. And so here my planet is as far away from the sun as it is going to get, and so it's traveling rather slowly, and as it picks up speed as it goes towards the sun, and then it gets slingshot around the sun, and it slows down and speeds up and then slows down. Now the difference in speeds for the Earth is not all that great from when it's at its apogee compared to when it's at its perigee or closest point. The other thing I should point out is we don't want to make a common rookie mistake for a physics person, the kind of mistake that an awful lot of people make because they're not very well schooled, and that is that when the planet is farthest from the sun, this is wintertime, and when it's closest to the sun, this is summertime. That is absolutely not true, because remember, the people on the other side of the planet have summer when we have winter. And then when over on the other side, they have winter when we have summer. So that is obviously not true that your proximity to the sun dictates when it is summertime. It has more to do with the tilt of the Earth's axis at 23.5-degree angle, so that one hemisphere is getting most of the sun. Let's say the Earth is spinning on this axis right there. So this side of the Earth is getting the direct rays of the sun. And then when the Earth is over here and spinning, the other side of the Earth is getting the direct rays of the sun. So this would be summer in one hemisphere, and this would be summer in the other hemisphere. The distance from the sun is, because it's not very much of a difference, it doesn't make a big difference at all. Now back to Kepler's second law. Because the planet is traveling more slowly here and traveling faster there, the same amount of time is taken when it goes from A to B as the planet is taking when it goes from C to D. So when you measure this area right here, it turns out to be the same as this area right there. That is the second law, and it's related to the conservation of angular momentum. You already know that linear momentum is mass times velocity. Well, angular momentum, which is in the next chapter, we use the letter L for angular momentum. We also use it in chemistry when we talk about one of the quantum numbers as being the angular momentum quantum number. And instead of mass, we're talking about inertia, which is the moment of inertia, or which is the position, the distribution of the mass, as opposed to the total amount of mass. We're more concerned about how the mass is distributed for a spinning object rather than how much mass it is, though we are concerned with that as well. And of course, instead of V, we use omega. So more about that in the next chapter. Now let's look at the third law. And the third law, we can go like this. We know that my centripetal force is equal to mass times centripetal acceleration. And we can also say that centripetal force is mv squared over r. Remember, we derived these equations in an earlier screencast as well as earlier in the chapter. And if we cancel out the mass of the planet, you can see that we get this right here, v squared over r equals the gravitational constant times the mass of the sun over r squared. And then we're going to come over to here. And if we continue to simplify this, and before I do that, I just want to show you another way to play with Newton's universal law of gravity. We have the universal law is right there. And this time I'm going to divide both sides by the mass of the Earth. And so I get this equation right here. And you will notice that my units are going to be the Newton per kilogram. And then if I look at these units over here, and I were to reduce those to their simplest form, I get the same thing. I get newtons per kilogram. And the point I'm trying to make here is that, therefore, we can take this term right here, and it's going to be equal to the velocity squared, right here, velocity squared divided by r. And the velocity is going to be the circumference of the sun, 2 pi r, and divided by the amount of time it takes to go around the sun, which is the capital letter T. That's called the period, the amount of time for the planet to go around the sun, and it's got to be squared, divided by r. And so when we then solve this equation for t squared, we get this mess right here, but we can simplify it because pi is a constant, g is a constant. As long as we're talking about our solar system, the mass of the sun is a constant. And all of those values together equal about 3 times 10 to the minus 19th. And let's just call that k. And so now we have the equation t squared equals kr cubed, where t is the period of time for the planet to go around the sun. It doesn't just have to be the Earth. And r is going to be that distance from the planet to the center of the sun. Pretty remarkable equation that everything would boil down to that. You can use this equation actually to calculate the mass of the sun, and I'll leave that derivation behind for the sake of time. But you'll notice that the mass of the planet becomes irrelevant because the mass of our planets is insignificant compared to the mass of the sun. And therefore, that would mean that t squared over r cubed should always equal some constant. And we can figure out what that constant is right there. So if we were to look at the radius and the amount of time it takes in seconds, I'm sorry, we want the mean distance, the average distance in its elliptical orbit from the sun, you can see that we pretty consistently get the number 3. Now, we can further simplify this if we invent a new unit. The new unit is going to be the astronomical unit. 1 astronomical unit, which is an AU, is going to be the distance from the Earth to the sun. So if 1 AU is the distance from the Earth to the sun, and we're going to be measuring the amount of time that it takes to go around the sun in Earth years, so we're making the Earth sort of the basis of everything. An astronomical unit is based upon the distance of the Earth from the sun, and the period is going to be based upon the time it takes for the Earth to go around the sun in years. We get t squared equals a cubed. And so when we look down, we're looking at this chart. This is, by the way, there is a space in our solar system that looks like there might have been a planet at one time that maybe blew up and produced an awful lot of debris. It happens to fit this pattern perfectly. So, our last problem, and then we're done with this screencast. Geosynchronous means we want a satellite that's going to be orbiting the same spot above the Earth. We want it synchronized with the Earth so that the planet is always above, say, St. Louis, or always above Jerusalem, or always above Moscow, or Tehran, or wherever else. If it's always above that place, it's in geosynchronous orbit. And so as the Earth is spinning, this satellite has to go pretty fast in order to stay above the same spot on that Earth. So our two problems are, at what distance from the center of the Earth would we find geosynchronous orbit? How far up do we like to put these geosynchronous planets and communication satellites? And what is the speed of that satellite? So we take Kepler's third law right here. You'd be given it on a test. We take his third law, and we're going to plug in our numbers. There's the amount of seconds in 1 year for one complete revolution. And here's our universal constant, gravitational constant. Here's our mass of the Earth. And we're going to solve this for R. And we find out that in order to be in geosynchronous orbit, you have to be 4.23 times 10 to the 4th kilometers, or 10 to the 7th meters. And then once we know that, we take that number, plug it in here, and since the distance around the Earth is 2 pi, the distance of the orbit around the Earth, not the surface of the Earth, but the planet going around the Earth, so the thick dot will be the Earth, is going to be 2 pi times the radius, 2 pi r, and then the period of time is this many seconds, and so we can see that the speed is going to be just a little bit more than 3,000 meters per second. So there are some variations to this. You might notice that the remarks here talk about Earth's sidereal period, because remember, while the satellite is going around the Earth is moving at the same time going around the sun. So we're not taking that sidereal time, the fact that the Earth has advanced a little bit, into consideration. Thus concludes Chapter 7.